Okay, so it's a pleasure to have with us our very own Jacob Richey, a new postdoc, came here just recently from Seattle, and he will tell us about some work on activated random walks. So, Jacob, all yours.
Yeah, thanks for the intro and for the invitation to speak here. Yeah, so I'm going to tell you about this model that I've been thinking about for 3 or 4 years now, activated random walk. And everything I'm going to talk about today is joint with Riddhi Basu and Srishendu Ganguly, my PhD advisor Chris Hoffman, and Leonardo Rolla. So yeah, let's get into it. So what is this activated random walk? It's a random particle process. There are going to be many particles on a graph. And if you've heard of the abelian or stochastic sand pile, those are its close relatives. So in general, let's take a vertex transitive graph G. You can think ZD if you like. And then there are two parameters that go into the model that I'll call mu and lambda. These are the density and the sleep rate. So let me say what all that means. So like I said, there are going to be many particles. The initial condition is every side of the graph starts with a random number of particles. And it doesn't so much matter what the distribution of the number is. Let's just, for this talk, let's just say it's IID Bernoulli mu. So every site starts with one particle with probability mu and 0 otherwise. So, okay, I guess I'm preemptively assuming that mu is between 0 and 1, which is all we're going to really care about. These particles are all identical, and they can be in two different states. They can be active or sleepy. Active particles do simple random walk on the graph at rate 1. So this is continuous time. They jump at rate 1 always to a uniform neighbor. Active particles can fall asleep. They do so at rate lambda. And sleepy particles, they're asleep, they don't move. And then what's kind of the final interesting rule, how do particles interact? When you have two or more particles at the same site, then they all become active. So in the simplest case, when there's a sleeping particle at some site and an active particle comes along and reaches the same site, then those sleeping particles woken up, and then they both continue their simple random walks. So just to show a little example, picture example, say this is our initial condition. Okay, I guess I said Bernoulli mu, but maybe here I started with two particles at site -1. Maybe this is somewhere in the process. This is the configuration on this interval. So maybe the first thing that happens is particle at site 0 goes to site 1 and then falls asleep. And then maybe one of the particles at site -1 goes to site -2, and then this particle at site 2 goes to site 1, and it would wake up that particle, and so on. So that's the dynamics. So why is this interesting from a mathematical perspective? This belongs to a relatively small class of models that has a particular abelian property. And you can view it as a kind of as a cellular automata. So what's that? You imagine that at each site of the graph, you have like a little robot, some black box operator that takes particles as input and then uses some function that can maybe be random to decide when to spit out the particles. I don't want to go into the details too much, but basically there are not so many models that that have an abelian property when viewed this way, that have some randomness, that have independent, or that have identical automatons at every site. These are also known as these chip firing models, and that have this abelian property. So activated random walk is one of these. Another is the stochastic sand pile. It also has an absorbing state phase transition. That's a good buzzword. So then that's what I'm going to talk about today. That's kind of the main thing we want to understand. There's a phase transition in the density mu of particles. So let me describe that in a bit more detail. And this holds, yeah, like I said, I'm going to focus on ZD. Actually, for today, I'm really just going to talk about Z for the second half. But this part holds on any vertex transitive graph, infinite vertex transitive graph. So the property, the behavior that I'm interested in is called local fixation. So I say that an instance of this process fixates locally if every vertex is only visited finitely many times by active particles. Okay, I can't hope that there's some time where everything is asleep. That's not going to happen because there will be particles that have arbitrarily long lifetimes. But I can ask for this condition that there's some, maybe it happens that over time there's some growing region of sites that are never visited after some time. Okay, so I call that local fixation. And if this doesn't happen, I say the system stays active. Or it does not fixate. So I want to understand the probability of this event. How does it depend on my two underlying parameters? So okay, there's a 0-1 law here. So you have this vertex transitivity, then you get the 0-1 law for you have some ergodicity. So probability of fixation is either 0 or 1 for any fixed mu and lambda. And there's also a very natural monotonicity in the density mu. If the system fixates for some value of mu and I decrease that, then it still should fixate almost surely, right? Intuitively, pretty clear. If I take particles out of the system, it makes it easier for things to fall asleep. And actually you might think that there's also monotonicity with respect to lambda, the sleep rate, right? If I increase the sleep rate, so particles fall asleep faster, also intuitive that you might think, okay, that also should make it easier to fixate, but this is open, don't know how to prove that yet. So it's not as obvious as it might seem. But that should be true. But that's okay. I only need the monotonicity in the mu to get my phase transition. So combining the 0-1 law and the monotonicity, I get this critical density. If I fix a lambda and I vary mu, there's some threshold that I'll call mu c, so that I have fixation below it and non-fixation above it. And you notice I wrote that mu c is in 0-1. It's not too hard to see that if mu is bigger than 1, then the system doesn't fixate. And you can prove this in a very general setting. If there's more than one particle per site on average, then it's pretty easy to see that you can't have fixation. But a priori, it could be 1, it could be 0. This could be trivial. So let me give a little more motivation, physical motivation, where this comes from. And that's this idea called self-organized criticality. So a slightly different version of the process has this feature that I'll show you a simulation of in a second. It's called the finite-driven dissipative version. So what's self-organized criticality? It's this property where the system evolves to a critical state without much dependence on the initial condition. More formally, in the statistical physics literature, it's a statistical property called power law avalanches at criticality. For activated random walk, you can think of that like this. Think of it this way. If you have some configuration of sleepy particles and you add a single active particle and you're at the critical density, so that many particles are sleeping, you add one active particle and you kind of look at how long this, right, that causes some cascading effect. It wakes up some particles, it wakes up some other particles, you get this avalanche, quote unquote. If the distance that avalanche travels obeys a power law, you say it has power law avalanches. And that was, yeah, if you look at the statistical physics literature where this self-organized criticality idea, I think, comes from, That's their marker for identifying this property. Some other features are okay, I said the minimal dependence on the initial condition. It also has long correlation lengths in time and space between particles, right? Once an active particle wakes up a sleepy one, they're kind of statistically linked over large distances. There are lots of interesting real-world models. Forest fires is kind of a nice one that's also been studied a lot in the probability literature. Just to describe that one briefly, imagine taking some large plot of land and dividing it into a bunch of cells. And the cells can be in 3 possible states. It can have a tree, it can be on fire, or it can be arid land. And then there are some natural transitions between these states. Trees can spontaneously catch on fire by being struck by lightning. Fire is more likely to stay on fire if it's surrounded by trees. I think it's something like this. If it has fuel to burn. And if fire is not surrounded by any trees, it's likely to just turn into arid land. And then an arid cell can sprout a tree with some small probability. This is kind of a prototypical system that has a self-organized criticality, because what happens if there's a very small density of trees, the density tends to increase. Right? If it's mostly arid land, then the density of trees will go up. But if there are too many trees, then they're likely to start catching on fire, and then the fire will spread and decrease the density. And so you can see it's kind of tuning itself. It's slowly converging to some critical density of trees. So that's what's meant by, that's kind of the simplest thing you could mean by the critical state is just a critical density. So what version of activated random walk does this? Yeah, I was saying this driven dissipative version. So what's that? It's basically the same as what I told you for an infinite graph, but now I'm going to run it on a finite graph, and I'm not going to have mass conservation anymore. I'm going to kill particles that hit the boundary of this box. So I start with some initial configuration on a large box, minus nn to the d. Yeah, let's say I start with my IID condition like before, but it doesn't really matter. I do the dynamics I said with this extra rule that particles that hit the boundary, I lose them from the system. This is a finite system, so eventually everything will fall asleep. When that happens, I just add another active particle at a random site and continue. And just repeat this. So let's, yeah, I'll just show you a simulation of that. Okay, so I started with, and I'm plotting the density here. So I started with density 0.25 particles on average per site. This is a 35 by 35 box in Z2, obviously. And the sleep rate's 1. So that means, when a particle moves, it has chance a half to fall asleep. Blue is sleeping particles, and then red is active particles, and the deeper the red, the more particles there are at that site. And then, yeah, I'm plotting the density over here. So you see, I started at a quarter. It quickly is increasing because I'm below this critical threshold. When I add a particle, it's very unlikely that it causes some particle to fall off the edge, and so the density just goes up by 1. Or the total number of particles goes up by 1. But then eventually we'll hit a point where those two forces balance, where when I add a new particle, the probability that it knocks something off the edge is the expected number of things that are knocked off the edge is exactly 1. And so our density will start to fluctuate around there. It's kind of silly, yeah. So I just moved here. I actually just got a really beefy new PC, but it doesn't have a camera yet, so I'm forced to run this on my little laptop. But I guess it lets us see. If I was running it too quickly, you wouldn't be able to see what's going on. So, but anyway, yeah, there we go. So you can kind of already see the density starting to already went back down, and it's going to fluctuate here around the mean. Yeah, so just to show, so there I clearly started below the critical threshold. I just want to show what happens when I start above it. So here I started with 0.6 density. Basically, I'm not going to run this for too long, because what's going to happen is it's going to take a really, really long time to, well, okay, I didn't start too far above the critical density, but it's going to take a lot longer for everything to stabilize. And we'll see a theorem that actually kind of proves something like this on, not on Z2, but on the ring. That if you start above the critical threshold, you have a very long time to fixation. Yeah, so you see, I started with all these active particles. It hasn't even stopped running yet, right? I haven't gotten to phase 2 yet, where I add a new particle because things are still active. But okay, I guess that just happened. Okay, that's enough simulation. And this picture suggests a lot of natural questions. I talked about the critical density mu c for the infinite system, but you can ask about, does this critical density exist? What is it for the finite system? As the size of, some limit as the size of the box goes to infinity. What's that? Yeah, how quickly is this density converging, either in the size of the box or in time? And what are these fluctuations we're seeing about the critical value? A very hard question, but one we're definitely interested in is, yeah, overarching kind of theme that we want to think about is what is this distribution of particles? Is there some stationary distribution for this Markov chain, this critical state? Can you somehow describe that? Those are really the overarching things we want to think about. Some more concrete things that are maybe more within reach. What is this time to fixate? Like I was saying, if you start with these active particles, some configuration of active particles, how long does it take before they're all asleep? Can you understand the odometer function? So that's a common thing to look at for these sorts of systems. That's the function that counts how many times is each site visited by active particles. Can you describe maybe the local behavior or the global behavior of that? What's is it? What's its distribution at a single point, or what's its distribution as a random function on your graph? And then, like I said, yeah, so there's this, can you even prove that there is a stationary distribution for this thing? As the size of the box grows, or in what sense is there some universal stationary distribution for this? I think some of these are difficult questions, but maybe, yeah, these are things I would like to think about, that I am thinking about. And just to relate these two pictures, the infinite and the finite pictures that I showed you, right? I had these two different, I used different letters because they're different. One for the infinite system, the mu c, and this other one, zeta c, for the for some limit of the finite driven dissipative systems without mass conservation. Conjecturally, these should be equal, and there should be an equivalence between these two properties that we're seeing, the absorbing state phase transition versus the self-organized criticality. These are two manifestations of the same thing, but again, all conjecture, sort of, we don't, this is just a conjecture that these two critical densities are equal. Great, so yeah, so now I want to move to some results. I'm going to share a bunch of results, show you kind of what we know, give it a little picking of what we know, and then I guess we'll take a break, and I'll come back and talk about a bit more in depth about some of the proofs, some of the ideas. So yeah, I'm going to focus on Z for a second, where the picture is not even completely solved. So the first big result about this critical density was from Rolla and Siderovicius in 2012. They gave a lower bound on the critical density. So they showed that mu c is at least lambda over 1 plus lambda. So you should think of that as a fixation result. They showed that for mu strictly less than this number, the system fixates almost surely. The next result, kind of on the other side, showing activity, showing the existence of an activity regime, is from Basugin, and Hoffman, 2015. So they showed that, this is sort of a cute way to say it, that mu c goes to 0 as lambda goes to 0. If that's a bit hard to decipher, I'll show a picture in a second that hopefully make it clearer. But what they really showed is that for any mu, even if mu is very small, so even if the density of particles is very, very low, you can take the sleep rate also very, very low so that you have activity. That's what this result is really saying. So even if there's one particle in every 1,000 sites, you can take the sleep rate to be extremely small, so particles only fall asleep, every 1,000,000 steps, so that the system does not fixate, stays active. And then this most recent result from myself and Chris Hoffman and Leo Rolla, we just submitted this a couple months ago. We kind of reversed the parameters in that last theorem. So this is also an activity result. We're showing the existence of an activity regime, but with the parameters reversed. So we show that for any lambda, the critical density is strictly less than 1. So even if the sleep rate's very high, particles fall asleep almost instantly, you can take the density very, very close to 1, but strictly less than 1, so that you have activity. Yeah, so like I said, I think it's easier to look at this picture. So on the right is the predicted phase diagram, so the density is on the x-axis, the sleep rate's on the y. Either for high density or low sleep rate, you have activity down here, or for low density or high sleep rate, I'm not sure if I said that right, but you have fixation up here, and then there's this critical curve between them, so that's predicted. What are these three theorems actually saying? The first one says there's some fixation regime above this explicit curve up here. And then we have some activity regime. The 2015 result says that this activity regime extends all the way down to this corner, this bottom left corner down here. And the 2020 result says that it extends all the way up to the top right corner. So that's maybe an easier way to think about it. Yeah, and these curves are explicit, but probably not anywhere near accurate. There's something like exponential. But actually, yeah, this lambda over 1 plus lambda also probably is not that accurate. There's a really recent result showing that near 0, the slope of the true critical curve, I guess I didn't draw it like that on this right picture, but it looks like a square root near 0. So mu is roughly like square root lambda near 0. So. Cool. So, okay, a couple more results. So that was on Z. This next result is on the ring. So if your graph is finite ring, Z mod NZ for large N, what's the analogous thing to look at here? Like I was saying before, you want to look at how long does it take for the system to fixate. It's finite, right? So everything will fall asleep, assuming you didn't start with more than N particles. So let's say T is the first time where everything is asleep. So we showed with Richey and Shishendu and Chris the existence of two different phases, two different regimes for this picture. If mu is small enough means, again, less than this lambda over 1 plus lambda, then you have a fast fixation regime. So the time is like log n squared. Probably you can get rid of this square. I'm not sure. Yeah, maybe it should just be log. But okay, so but that's fast fixation. And then on the other side, there's some activity regime. So for any mu, you can take lambda small enough so that the time to fixate is exponential in n. It would be nice to sharpen this transition a bit more too. But okay, this at least shows there are these two different phases where you have drastically different behavior. For some values of mu and lambda. Okay, if this all seems a little dire, like, oh, I can barely say anything about this critical density even on Z. I just wanted to mention a couple results where you can say quite a bit in slightly different contexts. So there's a very nice paper from 2015 of Stauffer and Taggi. They look at graphs where you have a little more assumption, an extra assumption about simple random walk there. So if you're on a vertex transitive graph that's transient, then they recover that that first condition. So activity, right? That critical density goes to 0 as lambda does. So existence of active phase for small density. And additionally, if the simple random walk on your graph has positive speed, so trees, for example, some trees, then you get the other side. Then you get also an active phase for any lambda, that the mu c is strictly less than 1. The methods there are quite different from what you end up doing on Z, but they're interesting. Another situation where you can say almost everything is this totally asymmetric random walk. So this paper of Cabezas and Rolla Sidervicius. So if you're on Z and you have totally asymmetric particles, meaning the simple random, the underlying random walk is no longer random, it's just particles always jump to the right. There's still randomness in the system, right? The initial configuration is random and the sleep times are random. But okay, in this case, they're able to show the critical density is exactly this lambda over 1 plus lambda. And they're able to say quite a bit more. They can understand pretty precisely the flow of particles across a single site, the odometer function at a single site. It scales to a nice Brownian diffusion, I think. Yeah, so I think that's it for the first half. So I guess we'll take a short break and then come back and do some more technical stuff. What should we say? 10-minute break? 5-minute break?
So we can do a few minutes, 7.
7-minute break, okay.
Yes, so I think we can take questions at this time. And are you planning to discuss the lambda over 1 plus lambda in the next part?
Yeah, it'll come up where this number is coming from.
Okay. Then I won't ask now.
What's that?
Then I will not ask about it now.
Yeah, it'll become pretty clear, I think, where this is coming from. But you can probably, it's not too hard to kind of guess. Maybe. I guess I've only given the continuous time description of the model. So if you think about the discrete time version, then this is a natural value.
Yes, okay. Right.
Jacob, I had a couple of questions.
Mm-hmm.
So if you look at different initial conditions, which are not Bernoulli, does the critical value only depend on the expectation, or is it more?
Yeah, so it's actually known, I think, in ZD for all D, that you can take any stationary initial condition and there's monotonicity with respect to the average density.
Okay. Yeah, I was thinking of just IID things, but more complicated than Bernoulli.
Yeah, no, it holds in great generality.
Monotonicity for the average densities?
maybe
Or do you need
stochastic
the stochastic domination of the initial states?
Exactly. Yeah. Sorry. Yeah. Exactly. So yeah.
Yeah, I mean, surely you do, because you can have average density 1 with everything asleep.
Yeah. Yeah. Everything has to start
you-
active. Yes.
But that still doesn't tell you that, say for IID initial conditions, that it only depends on the expectation, does it?
What do you mean?
Probably does not.
Oh, that was my question though. So, because you said at some point if the expected value is greater than 1, then it's easy to see that it stays active.
Mm-hmm.
And I was just wondering how the initial condition affects the critical value. So it's not just its expectation, it's relevant.
No, it is. It is. So if you have two initial distributions, you know, these shift invariant distributions where the average density of one dominates the other, or where one dominates the other, right? So I forget exactly how this theorem. Let's see.
Okay. Yeah, but if you can't compare them, if they're not comparable, then.
Yes, yeah, that's right. So one of them has to dominate the other, and then you get.
Okay.
If the larger one fixates, the smaller one does. Yep. I think I could be misremembered. There may be, maybe there's some kind of other moment condition or something, but I don't think so. I'm thinking of. Well, I guess I won't go look it up now. I can look at it later.
Yeah, so I see that Leo is here, so can also. So if you misrepresent anything, you can get a fast correction. So I guess the expectation on the ring is that you transition to exponential fixation time at the same u as the critical.
Sorry, what was the question?
So the expectation concerning the fixation time on the ring.
Uh-huh.
So would the conjecture be that you transition from logarithmic to exponential at the critical mu, the mu that is critical for z, for the infinite line?
Yeah, I mean, right, there's going to be some window as a function of n where you have logarithmic expectation below this. There's some critical window, and it's not clear how that depends on n. But
the size of the window, you mean?
The size of the critical window, yeah.
Yeah, that's.
But
that certainly would be more delicate. But at the moment, you don't even get a sharp transition, right?
right,
if I remember the theorem that you stated.
There's only on
there's
the
a gap where it's
only on the lower side is there kind of a, and it's not, yeah, I suppose it's not even clear that this is the right threshold. So
you see, and the log squared is the correct behavior there.
Like I said, yeah, it may be log. The log squared is kind of an artifact of step in the proof, as you'll see. Yeah, I'm not exactly sure. I haven't done extensive simulations on that one, so I'm not exactly sure.
there is some discussion in the chat about coupling for different densities.
Yeah, so how do I look at the chat from here? I can't, I'm inept. Can't seem to find the
So,
chat.
If
Guess
you're
I have to
sharing the
stop
screen,
sharing, or
you might not see the main window.
I'll take a quick look.
I'm not sure if you have a way of doing both.
Yeah, it's what Leo says. Yeah, so yeah, I forget what that. Are you a co-author on that paper, or is that that's you and Zindi, right, and Sitter Vicious, Leo? Yeah, maybe we can go link this paper later or something if people want.
Yes, log squared, that's true. Second.
Log squared is the order of time needed until all edges are crossed if lambda is 0.
Right, okay, so.
Right. Yeah, I suppose it's similar.
Okay, so.
Should we, continue?
Yeah, if there are no other questions, we can continue with the second part.
Okay. So yeah, okay. So yeah, now I want to dive in a bit and tell you how you actually analyze this thing. And the first step is to switch from this continuous time version to a discrete time version. So we use the following construction, which is called the Diaconis-Fulton representation. And the idea of this construction is to remove the randomness from the particles and instead put it in the sites of the graph. So the sites will form some random environment and particles just move through this environment. It's similar, but I think different from the chip firing version. So, okay, so how does this Diaconis-Fulton representation work? At every site of the graph, I'm going to have an infinite stack of instructions, IID instructions. These instructions can take many values. They can, some finite set of values. They can be either sleep instructions or a move instruction, move to one of the neighbors of that site. And these are random. They take these values with probabilities corresponding to the lambda. So these probabilities here, that when this instruction takes a move value, it takes all the neighbors equally likely, and the probability that it takes a sleep instruction just corresponds to that lambda, so that these rates match up properly. So at every site I have all these instructions, and now how do I evolve the system? The jth time a particle reaches site V, that site hands it instruction psi Vj, and the particle just obeys that instruction. So picture it like this. I have my configuration of particles, and then each site has this big stack, and one by one particles are coming to sites, and the sites are just handing out instructions as the particles come. Okay, but what does this really mean? I mean, I can't just do this all simultaneously, or like, what if there are multiple particles at a site? Who do I give, what instruction? What does this mean? The way it's going to work is I'm going to pick one site at a time, and I'm going to pick this site and say, okay, you give whoever's there instruction, and that site, and this site, and so on. So I specify some sequence of sites where there are particles. There's a problem, an immediate problem. What if the order makes a difference? What if I use this sequence or I use that sequence, then the resulting configurations are different. In one of them, maybe I get fixation, one of them I don't. Wouldn't that be a problem? something like that. Well, in a certain sense, the order doesn't matter. This is the abelian property that I talked about earlier. So if you start with any initial configuration of particles, and you look at some finite sequence of instructions, some finite sequence of vertices that you want to topple, that you want to give instructions at. If you take any reordering of that sequence of instructions, and you apply both of them, the sequence and some reordering of it to the same initial configuration, the outputs are the same. Assuming that both of the sequences of instructions are legal. And what does legal mean? It means I can't ask a site to hand out an instruction if there's no particle there to receive it. So things like that. Okay, so that's the abelian property. And so it basically says we can choose whatever order we want to evolve the system, and the end result will be the same. This is the key kind of thing that lets us use all the probability tools that we love to use. We get to choose very clever sequences that let us corral the system into doing what we expect it to. And so for the rest of the talk, I'm going to show you a few ways that this gets implemented. So the first result I want to talk about is the first one I mentioned previously on Z, this fixation result that activated random walk fixates for small enough mu. And the sketch is I'm going to have the particles fall asleep one by one in traps that I'm going to set up for them. So here's how that works. So we're on Z. Let's let xk, but xk is going to denote the position of the kth particle to the right of 0. So I'm only looking at particles to the right of 0 for now. So in my initial condition, the kth particle to the right of 0 is at xk. I'm going to find traps for these particles that I'll call, the trap for the particle xk will be called ak. I'm going to use some recursive method where I kind of explore the stacks to find these traps. So how does this work? I start from x1 and I'm going to send a little ghost particle, x1's ghost, out into the world to explore the path that x1 will eventually explore, will eventually do. So I send a ghost out from the position x1. It follows all the stack instructions that x1 would if we repeatedly handed x1 instructions at whatever site it's at. So that's the procedure I'm using. Just follow x1 around. With one additional rule, I'm going to ignore sleep instructions. Remember, I'm trying to show that the system fixates. So okay, this takes a bit of work, but if I ignore sleep instructions, that should only make my life harder if I'm trying to show that the system is fixating. So I follow this ghost around. It does its simple random walk. When it hits 0, I stop, and then I backtrack. I go to the right until I find the first site where the second to last instruction seen by the ghost was asleep. So in the picture here, the X's are sleeps, the arrows are the move instructions. So if you look, this site is the first one, the closest one to 0, where the second to last instruction was asleep. That's where I set the trap. And then I repeat. So then I go on to X2, send out a ghost from there, have it explore the stack of instructions as it would, taking into account that some of the instructions have already been explored by the X1 ghost. That ghost stops when it hits A1, and then again it backtracks for the first site where to the right of A1, where the second to last sleep instruction there was asleep. Okay, and I just repeat this. So this sums up what I just said. This recursive procedure where I find traps, find my traps AK. And so now how is the system actually going to evolve? One by one, I'm going to topple the particles the way they're basically going to follow the path of their ghost, with one caveat. that final sleep instruction that we found at the trap, you know, it was the second to last instruction that the ghost saw. The actual particle is going to ignore all the sleeps except for that one. When it hits that one, it actually obeys it and falls asleep at the trap. So assuming all this stuff makes sense, and to be fair, that's kind of where the hard work in this paper is. But let's do the fun part. Why does this show that the system fixates? For as Omar was asking, for our range of parameters that we're looking at. Well, the trap setting succeeds if I can always set my traps, right? There would be a problem if the traps were growing faster than the positions of the particles, right? Then I would have no space to set the trap for the kth particle without it bumping into the k minus first particle and waking it up when it's in its trap. So that would be a problem. So I need this condition. I need that ak minus 1 is less than xk for all k. Well, on average, the interdistances between the xk's, right, the particle density was mu, so the interdistance there is 1 over mu. And what about the traps? To find those guys, I just was asking about a particular instruction at some site being asleep. So the interdistance there is just the inverse of the probability that a given instruction is asleep. So by the law of large numbers, xk is roughly k times its mean, and same for the trap. And so this tells me that for k sufficiently large, if this condition held, if mu is strictly less than lambda over 1 plus lambda, then this condition does hold. The trap setting makes sense for sufficiently large k. And now you just finish by a standard kind of truncation idea. This tells me the probability of fixation is positive. So by the 0-1 law, it's 1. I suppose there's one last detail that I left out, which is that, okay, we only did this on the right side of 0, but you can do the same thing on the left side of 0, and again. Yeah, right, in this scheme, I never sent particles to the left of 0. Yeah, okay, so that was kind of the inspiration for a lot of future ideas, using the Sibelian property in this way to cleverly set up these traps. So next I want to show you how to adapt that to the result I presented earlier. This result on the ring. So I'm going to show the analogous thing on the ring, that for the same with the same relationship between mu and lambda, the time to fixate is like log squared. Okay, notice I wrote it a little differently. Now I'm writing that the number of stack instructions you need to fixate is like n log n squared. That's because I switched from continuous to discrete time. But this is the same result as before. Yeah, an important thing to note, I guess, you know, I was saying before how the initial condition didn't matter. Here it does matter a bit. This result wouldn't hold if you chose a crazy initial condition, for example. Not that this is so crazy, but it's quite different. If you chose the initial condition where all your particles were set up at a single site, then you know, obviously these have to spread out. It's easy to see that takes time, at least n cubed. So for this theorem here to hold, it matters that I'm using my IID initial condition, where the particles are nicely spread out. So the argument works in a couple phases. The first phase is to divide particles into small chunks that I'm then going to use a similar trapping procedure on. So the first step is I let all the particles just do independent random walk. Don't let them fall asleep. Wait until they hit a source vertex. So I have n over log n of these source vertices, and I gather roughly log n particles at each of them. So again, this is part of my toppling procedure, right? I'm saying topple each particle until it hits a source vertex and then stop. So that's phase one. So now I have these log n particles at each of these many sites, and I'm just going to do the same procedure on each block centered at the source. Okay. And it's a bit different now. So I want to do the same kind of thing. I want to find traps where the particles are going to fall asleep, but now I don't get to just send, particles indefinitely in one direction. They're emitted from the center, and they kind of go in two directions. So I have to figure out some two-sided version of this trapping idea. So that's what we do. So, but it's very, very similar. So I'm going to send ghosts out from the source, wait until it hits one of the boundary points, one of the previous traps that I've set. And then once that happens, so for this, say, I send this blue one out, it does a simple random walk until it hits the previous trap either on the left or the right. And then I backtrack toward the center. So then I walk a little bit in that case to the right, find the first site where the second to last instruction was asleep, and that's my next trap. And the trap on the other side just stays where it was. So, and now what do I want to happen? I want to make sure that I can set all of my traps before these two, the nearest left and right traps make it all the way to 0. So kind of what I want to happen is that I'm very balanced. It's not the case that when I send these ghosts out and set the traps that most of them are being set on the right instead of the left. In that case, the right would be shrinking too fast, and I wouldn't be utilizing all the space that I need on the left side. Yeah, you could. So a simpler version of this argument. You could do this pretty easily and get a much smaller threshold, like probably mu less than a half of that lambda over 1 plus lambda would be easy, I think. But to get all the way up to the same threshold, you have to be a bit careful here. So let me abstract that away and talk about this process, what's really going on here with these shrinking traps. The abstracted version is this process that is called internal erosion. So you imagine starting with an interval minus m to m. You start a random walker from 0, and you stop when she hits the boundary of the interval. And then you remove whatever point was wherever the random walker exited, you remove that point from your interval, and then repeat. So you have this eroding interval. And we want to analyze this. Can I somehow show what I was saying before? Can I show that these two sides are shrinking at roughly the same rate? And it turns out there's a very nice way to analyze this process, a nice coupling that lets you see what's going on. The idea is the following. Each unit segment in your interval, you're going to replace by a rope of some random length. So the part of your initial interval from 0 to 1, you replace by an exponential 1 piece of rope. The part between 1 and 2, you replace by an exponential 2. Generally, the part between j minus 1 and j, you replace by an exponential j. Same on the negative side. And then you attach all these ropes together. So now you have some very long piece of rope, like length m squared. And you initialize this process by lighting both ends of the rope on fire. And they burn at unit speed. And the claim is that there's a natural coupling between these two processes. So the key idea is the following, the one that's written there. So suppose in the erosion process, the original, not the rope version, the internal erosion process on the interval, suppose that you're down to some interval that's down to the interval from negative a to b. what's the probability now that you remove B? Well, it's just normal gambler's ruin probability, so it's A over A plus B. What about in the rope process? We're supposing that you're down to, well, the rope of length exponential B or exponential A on the left and exponential B on the right. What's the probability that the B one burns before the A one? Well, if you know your exponential random variables, it's simple calculation, you get the same thing. You get the same probability. And once the B length rope burns out, if that's what happened, conditionally on the exponential A rope being longer than the exponential B rope, because of memorylessness for exponentials, it has the same distribution. It still has exponential A distribution. And so this is the key step that you use to recursively show this coupling between the two processes. Okay. So yeah, this is from a short note by Lionel Levine and Yuval Perez. I don't think it's published. It's on Lionel's website. So they use this coupling to show the following pretty precise result. So you look at the number of sites remaining when the origin gets eroded. So eventually this erosion procedure does reach 0. When that happens, how big is the interval? They show that it's roughly order m to the 3/4, and they have a precise limit. For me, all I really care about is that this is sublinear, right? So what I was hoping for happened. I was hoping that they shrunk to 0 at the same rate. That's what this is. That's one consequence of this, right? It says when I reach 0 on one side, the other one is sublinear distance away from 0. Well, okay, this erosion was kind of an abstracted version of what I'm really doing, right? When I move the traps, they're not just moving unit distance every time. Like in the erosion process, they're moving some random distance, right? The inverse of this, of the interdistance between these, second to last instructions being sleeps. And these are geometric random variables. So we have to kind of repeat this idea, but with where the lengths of the interval segments are random now. And so you can see how this is getting complicated, right? You have these random length segments that you're then, if you want to use this rope coupling, now you're going to replace that by an exponential random variable with mean that is a random geometric, that's a geometric random variable. So the point is lots of concentration estimates arise here. But we were able to make it go through, and so and use this result to get what we want. So yeah, many concentration estimates necessary, but same result. So so we're able to set traps for all particles using this two-sided procedure and get the threshold that we wanted, mu all the way up to this lambda over 1 plus lambda. Okay, so that was all about showing fixation for the system. What about non-fixation? What about proving one of these activity results? So that's what I'm going to show you now. So this is the most recent one where we showed that I'm going to show that the critical density is strictly less than 1. So for any sleep rate, think of the sleep rate as being really, really high. So particles fall asleep almost instantly. I'm going to show that I can take my mu sufficiently large, sufficiently close to 1, but not bigger than 1, and have activity. So what's the main tool here? In the fixation case, we use these traps. So it was kind of a clever way to just literally show that things are fixating. Yeah, how do I check that the system doesn't fixate? So what we do is we use this lemma from the survey paper by Leo. Very nice survey paper. I might advertise for him. So this is a condition that we use to check non-fixation. So it says, if you're on some large interval, you start with your, usual initial configuration of particles. You run the dynamics and you count how many particles exit the interval after stabilizing, meaning after all the particles are either at the edge or asleep inside the middle. If a positive density of particles exit, so formally if the expected number of particles that exit is positive density infinitely often as the size of the interval goes to infinity, that's a criteria for non-fixation.
So this is for some arbitrary starting configuration?
I don't remember exactly what configurations are allowed here. Yeah, actually, I think in the paper we use a slightly different lemma from this. But Leo's saying IID maybe, or yeah, I think, yeah, maybe for this one IID is necessary.
Okay. Thanks.
Okay, so yeah, so how am I going to appeal to this lemma? So I fixed my lambda, which might be very large, and I'm choosing my mu very, very close to 1. The setup that I want to work with is this thing we call the carpet configuration. So I have don't ask me how I set this up, but imagine that the particles are set up this way, where I have a long string of particles. I mean, here I have 4, but imagine there are like 100 particles, 100 active particles, and then a single slot that I'll call a hole with no particles. And this just repeats. So actually what's happening is we use a random shift of this as our initial condition, and then I use a slightly different, a slight modification of the lemma I just showed you, but that's not too important. So let's pretend this is my initial configuration. I have this carpet with these occasional holes, and I'm going to show you I'm going to tell you how I run the dynamics on this carpet, and try and count how many particles are emitted. Right, a la the lemma, I'm trying to show that very many particles are leaving the block, leaving each little chunk of carpet and visiting their neighbors. So here's how the dynamics work. So let's look at one little chunk of carpet centered at a hole like this. The blues represent, I'm trying to show activity, so let's suppose they're all sleeping initially. Worst case sort of scenario. Okay, well, eventually some particle comes along and wakes up. It'll hit the hole, and on the way it wakes up at least half of the particles on one side. So my procedure is I'm going to give this guy an instruction. Ask him, do you want to sleep or do you want to move? Well, lambda was very, very high, so often this guy just falls asleep. In that case, I move the hole. So I move it 1 to the right. I want to keep it close to the center, keep it as close to the center as I can. So the hole moves 1 to the right. Then I do the same thing on this guy. Wake him up, say, do you want to move or do you want to sleep? Again, lambda is very high, so maybe the hole moves again. But eventually I find some particle that wants to do a move instruction. And when it does, I just repeatedly follow that particle for a while. It does some simple random walk excursion and returns to the hole. Alternatively, it could make it to one of the neighboring blocks. Like I was saying, it could be emitted to a neighboring hole. That would be good. That's what I'd like to happen. But if not, it just returns to the hole it was in. And on the way, it wakes up a bunch of particles, so I get to use those. Right now, I get to reset the hole back to the center of my block. And I just repeat this. So I'm leaving out some details, but this is the basic procedure that's going on inside each block. And I'm waiting for, I want this to kind of repeat over and over again. I wake up the particle that's in the hole, it does its little random walk. And I'm waiting for it to do one of these very long excursions to a neighboring block. So just to summarize what's going on here. Yeah. Okay, what could go wrong? It would be bad if things kept falling asleep. I want my nice configuration where there are many particles in a hole and then many particles in a hole. I want this configuration to stay the way it is. So if the hole moves too far, that's bad. So I want to somehow show that the hole stays close to the center. And the way we show that is to observe that it has a strong bias towards 0. Why? Toward the center of the block. Why is that? Well, if you know your simple random walk excursions, you know that it has infinite mean. So when the particle actually does wake up and take a step, with positive probability, it takes a step toward the center, and the distance it travels has infinite mean in that case. So even though with high probability, the hole is moving one by one to the right, with very small probability, it gets this infinite kick back toward the center. And we can use that to show that indeed, this is what's happening. It does stay close to the center. And while that's happening, I have many chances for this really long excursion to happen. For it to, be emitted to a neighboring hole, a neighboring block. So I kind of gave you the overview of what the dynamics are doing. The tricky part of the argument is kind of decoupling these blocks and making sure that stack instructions are being kept track of in the right way. So don't try this at home. Or, this is not exactly the hard part of the argument, but this is the key idea. So just to end, what would I like to do next? One thing we'd like to do is extend some of these methods to work for the stochastic sandpile, which is a related model, which I think sort of inspired activated random walk. And activated random walk is easier in some way because you have these random walkers to work with. In the stochastic sandpile, it's kind of like activated random walk with lambda equals infinity. Particles fall asleep instantly, but it's a bit different in that particles only topple when there's a pair co-located at a site. Anyway, so yeah, it would be nice to extend these results for that model, because I think even less is known about that one. As we discussed it, it'd be nice to sharpen this phase transition for the ring. And then another thing that's pretty well understood for other models is to understand, or for a couple other models, is to understand the odometer function on a finite interval. If you just start with n particles at the origin and you let them evolve until everything is asleep, can you say what the correct order is for the odometer function at 0? That seems like a nice kind of question that I would like to answer. Okay, so that's the end. I'll take questions.
So I think we'll unmute everyone to thank Jacob